Welcome to a lesson with Dr. Powell. Let's take a look at how we can solve a system of congruences using matrices. Okay, so we want to find a value of x, an integer, that satisfies all of these congruences. 4 mod 13, 5 mod 7, 1 mod 11. And this solution right here will be unique modulo the product of these guys. Now, essential to what we're going to be doing is we assume that 13, 7, 11, whatever numbers we put here, that they are relatively prime to each other. They don't share any common factors other than 1. Okay, so here we are. We're going to be using matrices to do this to help us out. All right, so first let's look at the first two guys. We're going to do this two at a time. So those two, let's do that. We can apply the Euclidean algorithm, looking at 13 and 7. So we're focusing on 13 and 7. And we think 7 times what gets us close to 13? What's the quotient? It's 1. The remainder is 6. The 7 into 13 is 1. Remainder 6. All right. Then we take the 7 and 6, and so this is the quotient. We're not going to reuse the quotient on the next line, but we're going to use these quotients in just a second. Okay, but on the second line we have 6 divided into 7 is 1, remainder 1. Okay, now let's look at these quotients. What we're going to do with those quotients is we're going to use them in a matrix as a matrix entry if we negate it. Okay, how does this work? Well, we want a function, or a matrix function, in column interpretation that goes from Z2 to Z2. That'll shift, see this 13 and 7, it'll shift it, so 13 and 7, it'll change it so that it becomes 7 and 6, or this 7 and 6 right here, the next line. So is there a matrix function that takes us from 13, 7 to 7, 6 based upon what we're doing right here? Okay, well, let's think about this for a minute. This one will do. Notice, notice here, for instance, we want to get 7, 6 out from 13, 7. Notice that see this 0, 1, what it does, if you think row interpretation, it picks out the bottom guy and puts it on the top. So it performs that shifting action. Notice this 1 minus 1, what it does is it takes 13 and then it subtracts 1 times 7. Notice what that, why does that give us 6? Well, think about it. What we've done is we've taken this 13, taken this 1 times 7, over to the other side, over here, so 13 minus 1 times 7. It's like we're saying 13 minus the quotient times 7 is equal to 6. So 13, and then here, minus the quotient, so plus minus the quotient times 7. So we can notice that the quotients in both of these cases are negative 1s. Negative 1, negative 1. And we can apply the same idea here. So to get a matrix that multiplies 7, 6, to give it my next one's in line, 6 and 1. 6 and 1. Now, what am I doing here, and why is this important? What we're doing and what we're setting up is we're trying to find quickly a sum of two things that equals 1, such that one of the things is a multiple of 13, the other guy is a multiple of 7. This idea will work, since what we can do is we can perform both shifts. So first, this one, which is right there, thinking column interpretation, this is the first function, then the next function is this guy coming over here. Matrix multiply those together, we get a shift that takes us from 13, 7 to 6, 1. But we're only interested in how we get this 1 from 13 and 7. In other words, it's the bottom row right here, dotted with this column right here. So negative 1 times 13 plus 2 times 7 is equal to 1. Aha! So that's what we're after first. That's the first goal. So we see this 13 and 7. The first goal is to get this right here, and we just did this using matrices. We're not done using matrices. There's more to do. All right, but first we got that. Okay. Next, we use the fact that this guy is equal to 1 to make a matrix that has determinant 1. Okay, see this negative 13 here, and then a minus negative 14. That's a plus 14 right there. It works. That's the determinant. Now, what is this? Now, this matrix is a isomorphism. It represents an isomorphism from Z2 to Z2. Determinant equals 1. And not only that, and it's a Z-module isomorphism, because it has an inverse with integer entries, its determinant being equal to 1. We know a few things. We can actually relate it to a quotient of Z cross Z, so Z2, and AZ cross BZ. I mean, another way of thinking or writing it down is we could just think of it as ZAZ cross ZBZ. So what we're going to do is we're going to take this matrix actually supplies us an isomorphism from this to now notice we're modding out everything in the first component. So it's like it doesn't even exist. So over here it's really like Z ABZ. So we're creating an isomorphism between this, a Z-module isomorphism, and not only that, it's actually a ring isomorphism. I mean, how does that work? Well, first of all, what we're modding out by right here, if we send it through G, we actually get what we're modding out over here. Think of that in a few different ways. First of all, there are A times B cosets of this and that, and same with this and that. So because of that coset equality, all we really have to show is that the image of this whole guy, in G, is actually contained in this other guy over here that we're modding out by. We show that, we're good. And we can see that simply by, okay, and what is A and B? So A, what are we modding out by here? So these are the congruents, the mods. So A is equal to, in this case, so going back to our original thing here, A would be like 13, we're modding out by 13. B would be like 7, we're modding out by 7. So really this 4, 5, you can think of that as being an element, after modding out, of Z mod 13Z cross Z mod 7Z. So 4 is in here and 5 is in here. So you have an over pair. Maybe you have some bars or arithmetic or wavy lines or something, whatever. 4, 5, something like that is an element of that. And so what we're doing is we're supplying an isomorphism that takes us here, and it'll give us, and it's taking us to Z mod 7 times 13Z, and that's 91Z. So we're creating an isomorphism, and what this is going to do is this is actually going to take this guy and output a solution to these congruences mod 91Z. Okay, which basically you just take that number and it'll be a solution to this, and you add any multiple of 91, and it's again going to be a solution. So this isomorphism G that we're developing with that matrix technique will actually do that for us. Okay, so going back over here, it's a ring isomorphism, so it produces, it preserves addition and multiplication and the identity. You can check it, just putting this into that matrix does output the 0, 1 here, and you can, by scalars coming out and going in, and this relationship as well, you can actually easily see that the inverse to this matrix is multiplicative, so this is multiplicative as well. It's a ring isomorphism. We'll just take that for granted for now. But one thing we have to check, right? we have to check to make sure that this, the image of this is really included in there. And you can do that rather simply by thinking, okay, we're working, what was it again? It was Zmod 13 and Zmod 7. So if we have, so for instance, if we put 13, 0 in here, that's, okay, so this guy right here, what we're modding out by, is actually spanned by 13, 0 and 0, 7. If you were to plug these guys into this matrix, you actually will get something in, here. I mean, try it, 13, 0. So you plug in 13, 0. It doesn't matter what you get in the top element, just when the bottom element, because it's AB, it just needs to be a multiple of AB. That's all I have to check. And let's see, if we have 13, 0 here, notice, so if we're plugging in 13, 0 as a column, 14 times 13, and yeah, that's a multiple of, that's so 13 and 14, so what's 14? 14 is 2 times 7, that's like 7 times 13, yes, it works. Okay, and that's general, and 0 times 7, if you put that in, that'll also be what we're after, a multiple of that AB, or 13 times 7. Okay, so the crux of the matter is it works. Okay, we have this isomorphism. All right, we've talked about it a little bit, but that's just so you kind of have a feel for what it is. But in principle, in practice, we just use it. We just get the matrix and use it. Okay, so we have 1, 1, negative 1, 14, negative 13. Now, how do we use this guy? How do we use this guy? Okay, so basically, well, we just plug it in. We plug it in the 4, 5. We plug it into this, and we're going to interpret the result, -91. And we're only going to take the bottom guy, because when we matrix multiply, we're going to get a column. But remember, we're modding out the first component, so we don't care about that. We just want the second guy. So 14 times 4 minus 13 times 5. Boom. -9, mod 91, and any, so -9 plus any multiple of 91, you can check, will actually be a solution to this. To this guy over here. That'll be a nice way of thinking about it. Now, why, you say, does that work? I mean, is it just because G is an isomorphism or ring isomorphism? Like, like how does that work? Well, let's just kind of think about it for a minute. All right. So -9 comes out, right? Now, where does -9 come from? Well, you can think about -9 coming out as being like, if you think about in terms of what's actually, you can think of this as being like a scalar. You put it out. The scalar will also be a scalar multiple over here, and you have the identity over here, 1, 1, identity representative in the domain. So this is like Z mod 13Z cross Z mod 7Z, and this is, okay, and this is a representation of, we're modding out the first component, so only focusing on the second component, but this is like Z2 mod Z cross 13 times 7Z. Okay, but it's going to be the same thing as Z mod 13 times 7, which is 91. So let's write that down. 91Z. Okay, so notice what's the preimage of this? It's this, but if you multiply this through, look at that. You have -9 in each component. So you're taking -9 and you're modding out by 13 and 7, and you should get 4, 5, which we already know, which we just showed is in the preimage, is the preimage of -9 because its image is -9. So that actually, there's the solution. -9 will be 4 mod 13 and 5 mod 7. It's one of the preimages is -9, -9, but guess what? There's only one preimage. This is an isomorphism. So so these two guys should be equivalent in the modding. So there, matrices. We did the okay, but wait a minute. We haven't finished the whole thing. Why not? Let's see. Because we had this original. We had 3 different congruences. We only did the first 2. So just to show you this doesn't take so long, we're going to keep going and finish it off just using the ideas that we've discussed, so we can get going here. All right. So next, Well, we've just solved the first two congruences, and let's just write that down as x is congruent to negative 9 mod 91. Okay, we still have left to focus on x is congruent to 1 mod 11. We just repeat this process. We end up getting these quotients, and this is like the first shift, second shift, last shift, as we're moving from 91, 11. All right, so 91, 11. So we have these guys. We matrix multiply these together. We get this matrix. And we take the last line to get the 1, which is this right here. Now we take these guys and we switch their order, like we take this guy and we put it here. That's negative 363. And this guy, we put it there. And then we just put a 1 and negative 1 just to make sure that this actually, the determinant's equal to 1. So 1 times 364, and then it's minus, minus, minus. So it's just minus 363, which is exactly what we have right here. That's minus 363. That's 364. Subtract them, you do get 1. Oh, that's great. So that is our matrix. And then what do? We just have to plug in that negative 9, 1 into it. We discussed a long time why we're going to do that and what the effect would be, but we're just going to do it right now. So plug in that negative 9, 1, and then interpret the result mod 91 times 11, which is 1001, and we get 628. And 628 will be value of x, and that satisfies this congruence and this congruence right here. And if you add by any multiple of 1001, it should all again be a solution. Keep in mind, see this this congruence that we had over here is also satisfied because, I mean, x congruent to negative 9 mod and 91 satisfies both of these guys. So, and we were assuming that it was that would be satisfied as well. And so 628 satisfies that, and it also satisfies this one. So we've just done it using some matrices. Thanks for watching.